So, how's everyone doing today? It is Friday. Let's see. Main objectives for class this Friday is finishing up the last little part of chapter 10. We introduced the Doppler effect on Wednesday. We're just going to do some math for it today, make sure that makes sense. And then we will discuss everything you need to know about the exam. Speaking of the exam, small announcement on that front. If you will gaze over to this board over here, I have changed what it says about the exam times. I have added, originally there was only the 3 that the school had originally scheduled, but I have since added 2 more. There's 3 options where you can take the exam on Thursday, December 7th. Let me put a calendar up on the board just so I have something to point at. So just to briefly discuss upcoming schedule again, today is Friday, December 1st. Happy December, by the way. Monday, we will have 1 more lecture together, which we'll spend reviewing and making sure everyone feels comfortable about the exam. Then exam season starts on Wednesday, and Thursday the 7th is the first day where you can take your physics exam. The 3 times I have posted for that are 8:30 a.m., 1:30 p.m., and 5:30 p.m. Those are the 3 possible times you can take an exam during the day, and on Thursday I will be here proctoring all 3 of them. You don't have to normally attend C period to come to C period. You can come to whichever one your schedule allows for that you want to attend. Separately, the next day, Friday the 8th, there are 2 slots where you could take the exam, that being 8:30 in the morning and 5:30 in the evening. So there's a total of 5 different times you can choose to take the exam. The goal is to offer you flexibility, because I always have students asking about, you know, I have 3 exams on one day, what can I do about that? Now, I will go ahead and say, I will not be proctoring the Friday sections myself. I have had something come up, I have to be out of town. Dr. Owens is going to be proctoring those. I will be proctoring all of the Thursday ones. So on Thursday, I'm just going to be here all day. So even if you're not taking it that day, if you have study questions, I will be in this building, camped out from about 8 a.m. to 9 p.m. giving exams and helping people. So just to give you all the relevant information about that. So those times are just going to stay there. I'll send out an email about them as well, because I haven't done that yet. And you may pick any one of them to take your exam. The exam itself, I have finished it. It is 16 questions, and of them, 5 are concept short answers. Only 11 of them are math. Try to condense things as much as I could. And I've already uploaded a practice exam for it. Again, main objectives for today are finish up chapter 10, make sure that you guys can do math for the Doppler effect. Then we will look at the practice exam, look at the list of concepts that you need to know for the exam, and then we'll break for the weekend, and on Monday we'll make sure everyone feels comfortable beforehand, before the exam itself. Yes?
Are you going to post a key for the practice?
I am, yes. That is what I will be doing today.
Did you pull a lot of stuff from our past exams for your final exam?
Yes.
So it's
The-
too similar?
Yes, the exam is basically just a long test. It's functionally test 1 and 2 crams together, but you know, things are compressed and shorter, and I've written it to account for you having a fixed time limit in order to do it. It's looking for your ability to understand concepts and use formulas. It's not trying to take ages and trick you. And it's written more like tests than like homework. Any other questions right now? All right. Well, let's finish up chapter 10, shall we? The last concept we talked about on Wednesday is the Doppler effect. This is the phenomenon that causes frequencies of waves, the perceived frequencies of waves, to change based on whether or not the source of the wave or the observer of the wave is moving. The place where I've mentioned that you would experience this in daily life is when a vehicle passes you, and you can notice the change in pitch of the sounds from the vehicle change as it approaches you versus as it moves away from you. You get that effect. Or as the object is moving closer to you, the frequency is actually higher than it should be. Whereas as it's moving away from you, the frequency is lower than it's supposed to be. And so at that moment it passes you, you get that change, the part. That is again caused by the Doppler effect. And this also happens if both either the source is moving or you, the receiver, is moving. Technically, you'd get the same effect if you were running towards the source of the sound and then passing and running away from the source of the sound. So it doesn't matter which is moving, as long as something is moving, there's going to be a frequency change. The formula that describes that frequency change is the one that's currently on screen. Frequency observed, this is the frequency that you hear as the observer, is equal to the frequency, the original frequency of the source, times, open parentheses, speed of the wave plus your velocity, close parentheses, divided by speed of the wave minus the velocity of the source of the wave. And we're going to review this to make sure every part of it makes sense. What this formula is again saying is, say an ambulance, just go ahead and put the numbers up. We're going to work a few examples of this to make sure that it makes sense. We're going to use the example of an ambulance. I mentioned I gave some poorly drawn pictures of that last time. The source of our sound is going to be an ambulance, and that ambulance's siren is designed to play 6,000 hertz sound. That is the sound it is supposed to make under normal conditions when standing still. And the speaker itself doesn't do anything different if the vehicle is moving or not, but whether or not the vehicle is moving will affect what you end up hearing. But the speaker itself is designed to output 6,000 hertz, and that's going to be the source frequency, because the physical speaker is designed to output 6,000 hertz sound. So in my list of variables over here, I will list f source as 6,000 hertz. And this ambulance is going to be driving along the road at a velocity of 30 meters per second. So that is the velocity of the ambulance. And since the ambulance is the source of the sound, that's going to be velocity source, because the source, the ambulance and the speaker, are moving at 30 meters per second. So, all this information so far is just describing the ambulance itself. It's emitting 6,000 hertz sound waves, and it's driving at 30 meters per second. If it was parked standing still, and you were just standing near it, you'd be hearing 6,000 hertz sound constantly. But it's going to be driving past us, and we're going to calculate how the Doppler effect changes what you end up hearing. You're going to so just to reiterate what's written on board, calculate what frequencies you would actually hear if you were standing still and the ambulance is first driving towards you and then driving away from you. If we are standing still, we are going to be the observer in this scenario. And since we are observing, our velocity is going to be v observer. If we are standing still, what is our velocity? Very good. You're the observer, our velocity is 0, so v observer is going to be 0. Now the just v, the normal letter v in that formula, stands for the speed of the wave velocity, the normal velocity of the sound wave. And we're going to assume, for simplicity's sake, that sound is moving at the normal 343 meters per second today. So, just v, normal v, is the speed of sound. That is the speed the waves are normally moving. And what we're going to be solving for here is f observed. What that variable stands for is what frequency of sound you are actually going to hear once the Doppler effect is done changing it. And so what this formula is ultimately doing is, it's taking the original frequency, multiplying it by a weird looking fraction that is sort of a ratio of the adjusted speed of sound based on the speed of the source and the observer. It's taking the original frequency, adjusting it slightly due to the Doppler effect, and then giving you the adjusted frequency out the other side. That is what this formula is trying to do. That is the purpose of each part of it. And now let's prove that it works. Any questions before we do that? Okay. So, we've identified all the variables we have and the one that we want. We're first going to work this as if the ambulance is driving towards us. So our formula, F observed equals F source times, open parentheses, speed of sound plus our velocity. I'm just going to write V obs for observer. Then V minus V source for the source of the sound. We know everything here except V observed. We're set to solve for V observed. First, we're going to work this as if the ambulance is driving towards us. So V observed. The original source frequency is 6,000. That is what the machine is physically designed to output. That's what it normally outputs in normal stationary conditions. So that's the original frequency before the Doppler effect changes anything. Just V, in both parts of this fraction, just V is again the speed of sound. Bless you. Bless you.
Thank you.
Welcome. And the top part of the fraction is adjusting the speed of sound based on our velocity. Now we're standing still, so nothing changes on the top part of this fraction. Our velocity is 0, so the top part of this fraction is just going to be 343 for the basic speed of sound. On the underside of the fraction, though, we need to subtract the speed of the source from the speed of sound. Now, the ambulance is drawing towards us, so that means we want to plug in a positive velocity for the ambulance, but we're plugging it into a spot that is inherently negative, so that ends up being 343 minus 30. This is important. The formula necessitates there be a minus sign here. We're going to plug a positive number in if the object is drawing towards us. Noted here, if things are getting closer together, you plug in positive numbers regardless of there being a negative sign here. And if things are moving away from each other, you plug in negative signs regardless of whatever sign is already in the formula. So since the ambulance draws towards us first, we're going to plug in positive 30, and it ends up becoming minus 30. And so what we're going to end up doing here is multiplying the original frequency by a fraction that will adjust it relative to the speed of the ambulance. First, I'm going to solve for that fraction. I'll simplify it a little bit just to try to show what I mean. The top part of the fraction, 343 plus 0, is just going to be 343. The denominator of the fraction, 343 minus 30, is going to become 313. So again, we're taking the original 6,000, multiplying it by this new weird fraction. This fraction, since the denominator is smaller than the numerator, if you solve for this fraction, it's going to be bigger than 1, right? And what that's going to do is it's going to increase the frequency that we're hearing. So as the ambulance draws towards us, it's decreasing the denominator, and that's going to increase the frequency that we hear. Because as the object gets closer to you, it's going to emit the sound waves closer together than it's supposed to. It's kind of like catching up to the waves it just made. That's going to smush together the sound's wavelength, driving up its frequency. Wavelength goes down, frequency goes up. And that'll become relevant in our final answer here. F observed, 6,000 times this fraction should give us a number bigger than 6,000. What does that number end up being?
6,575.
Thank you very much. And that is still in units of hertz. So the ambulance driving towards us has increased the frequency of the speaker by 575 hertz. That's like 9% higher. The sound is 9% higher pitched simply because the ambulance is driving towards us. That is a significant enough difference for the human ear to be able to perceive. If you want to check that for yourself, the makeup lab that I sent out has a link to a sound test in it where you can see how well you can hear given frequencies of sound. You could check yourself the difference between 6,000 and 6,575, confirm that it is a discernible difference. But just because the ambulance is driving towards us, that has driven up the frequency by a noticeable degree. Any questions on this first method, or this first conversion? All right. Now, we're going to do the same basic thing, but instead, the ambulance is going to drive away from us. Drive away from us. All that will really change is the sign we put on the 30, because if the two objects are getting closer together, it's a positive number we plug in. If they're drawing away from each other, it's a negative number we plug in. We're still going to stand still. We're not doing anything. But the ambulance, this is going to be the point where it passes us, and now it's moving away at 30 meters per second. So that's all that's going to change for this next part. Let me put this over here instead. Same base frequency, because the speaker's not doing anything different. And then the top part of the fraction isn't going to change because we aren't doing anything different. We, the observer, are still just standing still. Instead, the ambulance is now moving away from us, and so we plug in negative 30 instead of positive 30. That's going to end up being plus 30. So note again what sign is already in the formula, and then you have to plug in a specific sign based on the relative direction of the observer or the source. This, instead of driving the frequency up, is going to have the effect of driving the frequency down. Because now 343 minus negative 30 is the same as plus 30. So now the underside of the fraction becomes 373. Now the denominator is bigger, this fraction is less than 1, so this frequency is going to go down. What does the frequency drop to?
5,517.
Thank you. So now the sound dropped in pitch by about 9%, which again is a noticeable difference to the human ear. And what's really a noticeable difference is the difference between the speed when it's moving towards you, the frequency when it's moving towards you, and the frequency when it's moving away from you. That's a difference of 1,000 hertz, which is very distinct to the human ear. 1,000 hertz is like the difference between thunder and a low speaking voice, like a low pitch speaking voice. So that's really why the Doppler effect is very noticeable as the car passes you, because in that split second, the vehicle's only really next to you for a moment. It takes less than a second for it to move from driving towards you to driving away from you. So it takes less than a second for the sound to switch from that to that, and that's the really noticeable part, the meow transition. So that's why that happens. Questions? I will note that the same basic thing would happen if we were the ones moving instead of the ambulance. I'm gonna rewrite this to try to show that. Okay. Oh, come on. I tweaked the example slightly just to illustrate a point. In this version of events, the ambulance is parked and we're going to be the ones moving, just to prove that the other way still works. So don't erase anything. Don't erase your own notes. I'm just going to change what's on the board to represent what changes as a result of this. Instead of the ambulance driving at 30 meters per second, we are going to be running at 30 meters per second. Perhaps you're a superhero or a paramedic or just an ambulance chasing lawyer. So don't erase anything, I'm just showing the change. If the ambulance is parked and it's still the source of the sound, then now velocity source is 0 and our velocity is 30 meters per second. That's the main difference. We're just switching who the velocity is attributed to. So now, ambulance is parked, we are running at 30 meters per second, which is probably superhuman, so congratulations, you're very fast. What that's gonna do to our math is, the source is now 0, because the source, the ambulance and the siren, isn't moving, and we are. So now we are moving towards the ambulance. We still want to plug in a positive number if we're drawing towards the source. So now we're going to put positive 30 for be observed. We're still the observer even if we're moving. And now there's a 0 on the bottom for the speed of the source. And that's going to change the fraction to 373 over 343. That fraction is still greater than 1. Right? Now it's still a bigger number divided by a smaller number. So the fraction is still bigger than 1. And so the frequency might not be the same, but it's still going to be higher. Does that make sense? Now the frequency is not precisely the same, but it's very close and it is still higher than 6,000. So by running towards the source, the frequency still rises. This is because rather than the sound waves being made closer to each other, you are receiving them faster than you're supposed to. If you're running towards the sound waves, they're going to hit you and your eardrum faster than they are meant to, closer together than they are meant to. So that still decreases the wavelength and increases the frequency. Does that make sense? All right. Now we'll do running away from the ambulance, just to again show how this works. Ambulance is still parked. Now the main difference is we are running away from the ambulance. Say, drop someone off and now we're running away to go grab someone else who needs help. Again, we're superheroes. So now the fraction is going to change from, well, again, we're plugging in a negative velocity because we are moving away from the source. So now the top of the fraction is going to be 313, and the bottom is still 343 like it is running towards the ambulance version. That fraction is, once again, less than 1. That's still going to drive the frequency down. So regardless of whether the object is moving away from you or you are moving away from it, that still drives down the frequency, because if you're moving away from the source, the waves are still going to reach you further apart than they're supposed to, driving up wavelength and driving down frequency. And that will adjust the frequency slightly to 5,475 approximately. So still 1,000 hertz difference that you would hear between running towards and running away. So you'd still get the meow, but it's your speed rather than the ambulance's in this case. If you ever want to test this, you can set up a speaker playing a constant tune and try to run towards and past it as fast as you can. You might not be able to run at 30 meters per second, so it might not be as noticeable as this version, but if you pay as close attention as you can while sprinting, you might notice something. The effect is more dramatic the faster the objects are. That's why you walking doesn't really ever trigger this sort of phenomenon. You know, a difference of 3 meters per second wouldn't cause a very big fraction one way or the other. And walking speed is about 3 meters per second. No, walking speed is like 1 meter per second, sorry. So walking speed doesn't cause this very much. The effect is exaggerated the faster things are. So just something to note. Any questions about any of this math? All right. Last thing that I'll mention before we are done with chapter 10, just kind of as a fun fact. This phenomenon is utilized by every piece of human speed detection technology. What am I trying to say? The sign I need to drink some water. A radar gun, for example, something that's meant to measure the velocity of an object from a distance. What it's doing is it's emitting a certain frequency of wave, and it knows what frequency it's emitting. Like it might be set to 500 hertz, and it knows that. It's going to emit the wave at whatever object you're trying to measure the velocity of, even if the observer is standing, well, when the wave hits the vehicle, technically the vehicle re-emits the wave, so now it becomes the source. I'm not going to ask you to do the math for that, but basically when the wave hits the vehicle, it bounces back at an adjusted frequency because of the Doppler effect, and the gun is going to receive a different wave than it emitted. And using this formula, it can then calculate the speed of what re-emitted the wave. So what radar scanners do is they emit a certain frequency, they receive a different one, and they can calculate velocity based on how much it changed. So all human-built speed detection devices use this, and so too does every single echolocating animal. Echolocation doesn't just tell bats how far away something is, they can hear how much the frequency changes, because they know what frequency they scream at, and they can hear if the frequency changes once it returns. So they too can figure out not only how far away something is, but how fast it's moving, and whether it's moving towards them or away from them, which is useful if you're trying to catch a bug or run away from a bigger animal. Animals just do that subconsciously. Animals are smart. They're doing all this math in their heads. This works for light as well. You would just plug in the speed of sound, the speed of light instead of sound waves. If you've ever heard of like astronomers talk about a star red shifting or blue shifting, they're referencing how much the frequency of light a star gives off changes, whether it's moving towards Earth or away from Earth. So, it's useful for space people too. How you guys feel? Yes?
There's an example of what you were just talking about in the homework for number 7.
Yes.
And I'm trying to use that formula and I just can't do it.
Well, let's take a look. While I'm loading up the homework, I'll go ahead and mention out loud, there is chapter 10 homework, but there's not a chapter 10 quiz. The idea being, like usually I tell you to do the quiz after the chapter, and chapter's done now, but there's also exams to study for. So rather than make you do a quiz, I'm just saying, do the chapter 10 homework and then do the exam review. Was it number 7 you said?
Yeah.
Okay. Oh, right. Apologies, I may end up changing this example slightly. The issue here is, the bat is moving. So, the problem here is you have to do it twice. Once because originally the bat is the source flying towards the bug. And that means that the bat moving while it emits this frequency sound is going to adjust it in relationship to what the bug hears. But then, as a separate part, a second part, what happens when sound echoes is sound wave is going to strike something, be absorbed by the object, and then be re-emitted as a new sound wave. So every echo is literally the object in question absorbing some of the energy and bouncing some of it back. And so that means that when the bug gets hit by the sound wave, it absorbs it and then becomes the new source. Meaning that that's going to adjust the frequency again. So you'd have to do the equation twice. Once for what the frequency adjusts to because the bat's moving, and then again for how the frequency adjusts based on the bug's velocity upon re-emitting it. So I'm actually going to change this example. I'm glad you brought this to my attention. Because the one Doppler effect question that I put on the exam doesn't require you to do that, nor on the practice exam. So I will be changing this one in the homework. Sorry for that. Thank you for telling me. But the reason is it happens twice. So sorry about that. Yes?
Is the Doppler effect question on our exam kind of like this one?
Yes, it's more like, well, hold on. Let me find the thing. Can't tell you exactly what it is, but I want to make sure the information you have is as helpful as possible. Okay. The one time the Doppler effect comes up on the exam, and it's part of a larger sound question. Like one question out of 16 is about sound. Part of it is using the Doppler effect formula. So it's not a big part of the exam. It's just something I want you to be able to do. Notes. The one time it comes up on the exam is mostly like what we did here. Sound is emitted by a source, you are and the source is stationary. Sound is emitted by a stationary source, which means that P source is 0. You are moving towards it, so you have to factor in your velocity, and there's no bouncing around or rebounding. It's just emitted, you are moving towards it. What is the difference based on your velocity? So unlike the question on the homework that I'm going to remove, you don't have to factor in that it's an echo that the sound is rebounding or anything. It's just use the formula one time, adjusting the frequency once based on you moving towards the source. Does that answer the question? Okay. How do you guys feel? All right. Well, that's chapter 10, so that's the very last new thing I'd want you to know before the exam. Question?
On the homework, do we have to upload pictures?
No, you do not. Whenever it asks, well, hold on, let me check something. Whenever the homework asks for you to explain something or upload something, it's a computer. It can't actually grade what you send it. So that's really just a free point. You can type in sunflower here and it'll give you a free point. You can upload the last meme you downloaded and it would give you a free point. I usually try to make those things worth 0 points or edit them out when I can. In this case, I still need to do that. Well, I'm going to take this whole question out to begin with. But say number 3, the explain part, you can write anything here and get a free point, but you should still think about the explanation. Make sure what's happening makes sense to you. As we prepare to end for today, I'm going to load up Brightspace real fast. To show you the final exam tab. Here it is, final exam chapters 1 through 10. Like with the 2 previous tests, when you click on the tab itself, it brings up the full list of concepts you should be familiar with. This list is the same as the first test list and the second test list, but with 2 new entries from the last week. So the 2 things that I would expect you to be able to do on the exam from chapter 10, waves and sound, are 1, use the wave speed equals frequency times wavelength formula, and 2, use the Doppler effect formula. Actually, hold on a quick sec. Those are the only 2 sound wave formulas I'd expect you to know, but I would like you to know that sound is a mechanical longitudinal wave. If I ask you what is a sound wave, I would like you to tell me mechanical longitudinal. Mechanical meaning it is a wave that travels through a physical medium. It requires a physical medium, like how sound needs air for you to be able to hear it. And 2, longitudinal, as opposed to transverse. Sound isn't shaped like this, it's shaped like this. So there's 3 sound related things. 2 of them are math. I want you to be able to use these 2 formulas. And second, if I ask you what is a sound wave, I want you to tell me mechanical longitudinal. as opposed to electromagnetic transverse like light. Light is electromagnetic transverse, sound is not. Additionally, within this tab is the mostly updated practice exam. I actually want to add one more thing on it this afternoon before I make my answer key. The practice exam will be 23 questions. I'll point out again, the practice exam is always longer and more difficult than the actual exam. The actual exam is 16 questions, this is 23. So, when you look at this and you see 23, I don't want you to panic. The actual exam is technically shorter than the first two tests fused together. And again, my intent here was to contain every single formula and every single concept that could possibly come up on the exam. I've already finished the exam, so I know what's there. I knew what types of questions to put here. This afternoon, I'm going to add one more quick concept question. Again, making sure you know sound is a mechanical longitudinal wave. You do need to know that. And you need to be able to use, let's see, number 20 is Doppler effect. Number 19 is speed of sound equals wavelength times frequency. I'd recommend going over this over the weekend, and then we'll review it further on Monday. We'll use Monday to close out the week and close out the course and make sure everyone's feeling comfortable. Anyone have any questions, needs, concerns, etc. right now? Yes.
When is the makeup lab due?
Officially by next Tuesday. That's officially the last day that grades are supposed to be. I'm not supposed to give you anything due past that day. So officially, it's Tuesday, December 5th. That's when I need it by. Unofficially, make sure I have it before I submit grades on the 15th. Yes, you can email me.